Good afternoon. Am I audible? So, what topics did we discuss in our last lecture? What did we study? What did we study in our last lecture? So, we have discussed two algorithms, right? One was policy gradient descent algorithm, and what other thing did we study? Policy gradient method is one thing. Policy gradient method, and what else? You don't remember anything? That was the before class. So, we also discussed the contextual bandits, right? Yeah, within policy gradient method, we also looked at what is called actor critic algorithm, right? Where instead of just using a policy gradient method, if you also maintain a value, uh, like estimate of what are the true means of each arms in the gradient descent, instead of using the immediate reward as the sample gradient, we can use an estimated mean instead of immediate reward in computing the stochastic gradient descent. So it looks like everyone is kind of lost. So maybe I'll do a quick recap and then we'll. So if you remember, these are the topics we discussed in the last lecture, which are the policy gradient method and contextual bandit. So what are the motivations for policy gradient method? Like till now, whatever we have looked at are called value-based method. Before policy gradient method, we have looked at UCB, explore, then commit. All these algorithms are called value-based methods because they mainly estimate what is the expected reward of every arm, and based on that, they make some decisions as to what arm you should play next. So these are called value-based methods because you are estimating the value of each arm, and based on that, you are deciding your policy, what arm you should play next. So in policy-based methods, instead of estimating the values for each arm separately and then deciding which arm to play, you directly try to learn what is a good policy. Okay. So it is useful in scenarios where you have a continuous set of arms. Let's say you have infinitely many arms, and if it is not possible to go and find the value of each arm separately, let's say, then policy gradient methods will naturally be useful because here you are trying to define a probability distribution on the set of arms with what probability you want to play each arm. You're just having some parameterized representation of your policy like this, and based on that, you have some parameterized representation of your policy, which is represented by some set of parameters theta. And for a given policy, you are understanding how do we estimate, how do we understand whether a policy is good or not. How are we representing that? We are representing by theta, which is the expected reward if you play a particular policy. So pi of theta is a policy. Pi theta is a policy which is like a probability distribution on each arm. We are just seeing if you play according to pi, what is the expected reward that you are going to get. So that's what we are trying to maximize. It becomes a function of theta. Theta represents a particular policy. So now you are finding what is the best theta or the theta for which the expected reward is the maximum. So we used a technique called stochastic gradient descent where if you now you have a function of theta, you just want to maximize that function of theta. But the only problem is if you try to maximize that, we have to calculate the gradient of that function. Let's say you want to use stochastic gradient algorithm like this. But the gradient will involve the term Q of A, which is the true mean of arm A, which we do not know. So doing a gradient descent is not easy, is not feasible here. So then we looked at something called stochastic gradient descent. What is stochastic gradient descent algorithm? It is like a gradient descent algorithm where instead of using the gradient, you use some approximation for the gradient. The property that it should satisfy is the approximate gradient that you are using. If you take the expectation of that approximate gradient, that should be equal to your true gradient, right? So you need not use the gradient, but approximate gradient is equal to our true gradient. So then what we did was we calculated the gradient for our neta, which we defined. It turned out to be something like required. Then what we did was we have written that as an expected value. You are able to write the gradient as an expected value of something. So we don't know that value of the sample, what is inside this expectation, right? So that's what we did. We were able to put expected value equal to your gradient, and we know how to sample the inner part of that expectation, where it is nothing but RT and this is the parameter for your policy. We know how to differentiate them, right? So we'll just use this. And if you remember, we have mentioned two variants. One is you don't mention its value. What? The other version, which is called the active critic version, instead of substituting RC here, you substitute mu bar of AT, which is the estimate of your true, it is the sample estimate of your true mean. Okay. And this is a policy gradient algorithm. You just start with some arbitrary parameters. You play according to the policy, your current policy. You obtain some reward, and you just update your policy parameters using this stochastic gradient descent algorithm. So this was the policy gradient algorithm. And then, as I said, actor means policy network, and policy function can be treated as an actor because it is telling you how to act, what action you should take. Critic in this notation can be thought of as a function which tells you how good is your policy, how good is your action. Let's say that is like the value function. How good is a this is like estimating the mean rewards of the arms. So critic is like a value function which is telling you how good an arm performance is, and actor is like telling you which arm to play. So that's why it's called actor critic, because we are maintaining mu bar of 80, which is like a value estimate of every arm, and then we are also having a parameterized representation of our policy. Okay. And then we went into contextual bandits, which is until before this, we have seen only bandits where there was only one state, right? There was only one single state, and you'll always be in that state. You take any action, you get an immediate reward, and again you will be in the same state, right? The state won't change across time. In contextual bandits, it's a bandit problem with multiple states. You can to just visualize it in some practical scenario, you can think of it as a recommendation system where users are arriving to some website, and you are supposed to show some news articles to the users. So each user might like different news articles. So the probability of a user liking a news article differs with the user, right? Changes from user to user. So you can think of each user as a state and each news article as a arm, right? So now, depending on which user turns up, depending on the state that you see, that is, depending on which user turns up, you have to show different arms. You have to show different news articles, right? So that is the contextual bandit scenario. And so let's say there are 10 articles in your website which you want to show. So you can think of them as 10 arms in your bandit problem. And uh, every user you can think of as a state in your bandit problem. So one way to model the state is just model the state as some features of the user. So I'll model the state of a user as a three-dimensional vector like this. which is giving you some features about the user, like what is the location from which he is browsing, what is the age, what is the gender, or from what kind of a device is he browsing, whether it's an Android tablet or whether it's a desktop. So I can have some features for the user. So this can be your state. Now, your for every user, the property that you like a particular arm will change based on his features, right? So now the true meaning of a real number anymore, like not a simple real number anymore. It's a function of your user, right? The property that lets you define an arm name is a function of XU, right? So one way to look at it is you can think of it as uh, so if you have a lot of states like this, one way is you can cluster them into different groups. Like you can cluster all the users into multiple sets and treat each user as each cluster as one particular state. So all these kind of users will have similar likings. So you just categorize the users into multiple groups and learn one bandit problem on each user. Think each cluster as some state. So that is like how you can use unsupervised learning in relation to RL. So you first use an unsupervised learning clustering algorithm to cluster all the users into multiple groups and then treat each group as one particular state and learn a separate bandit problem for each cluster. That is one way you can use unsupervised learning. If you want to use supervised learning, as I said, you can model the true mean of the as a function of the features. Okay, so to start with, one can model it as a linear function of the features, right? So this is the true mean of a particular arm for any given user, right? Now, if you want, previously we were learning what are the true means for every arm, right? So if there are 10 arms, all that we wanted was 10 real numbers, like what is the true mean, estimated true mean of arm 1, what is the estimated true mean of arm 2, so on. Right now, our true means are functions of the user features, right? So it's not that you're going to learn one number, you have to learn this function, right? So what does learn this function mean? What should we learn? We have to learn these weights, W's, right? Because if you know those W's, then for any user, you know for that arm what is the true mean, right? User features will come when the user comes, you'll know the user feature. If you want to know what is the true mean of that particular arm for a given user, you can use this function. If you can estimate W1 exactly, then you know the true means. Then if a new user comes, you find you have the features of that new user, right? Then you find mu a of HU for all A's. For every A, you'll get a mean corresponding to that user. You see which arm has the highest probability of liking for that particular user and show that article. This is like a greedy algorithm. Like you can have epsilon greedy, you can have UCB, all kinds of variants in this one. Okay. So instead of having mu a bar, we have W1 a bar, like some estimates of, instead of having mu a hat, an estimate of mu a hat will have estimates of W1 a hat, W2 a hat, W3 a hat. What you do with that estimates is another thing. You can do all the different kinds of algorithms that you learned before. Okay. So one way to if you want to solve this problem, you know, so let's say there are only two arms. Let's say there are only two articles, and different users are coming to your system. And let's say you are initially doing some exploration. So some users are coming. Some 8 users are coming. First 8 users, let's say you are doing exploration. So user one came, you random so arm one 4 times. For the first 4 users, you show arm one. For the second next 4 users, you show arm two. Okay, then you can collect data like this, right? Okay, this is the first user who came, and I showed arm two. And this is the report that I got, whether he liked it or not. Okay, so this kind of data you can collect, right? This is like an exploration. You don't know anything about the arms. So initially, let's say you are exploring each arm for some number of times. So for the first four, let's say first 4 times, you are showing arm one. Then, okay, these are the four features who came initially, and these are the features of the user. And this is whether he likes that or not. This is like the reward that you got for showing that article to each of the users. Now you got some data like this. Can you estimate the functions, mu way of x for each arm? How can you estimate now? So this is like a feature. This is like a feature. This is an estimate of the function, right? Whether it likes, which was W like W transpose x, right? So now you have the instance. It's like a four linear equation, right? You have three unknowns, which are like W1A, W1 arm one, W2 arm one, W3 arm one. Like you have three for the first arm, and you have four equations, linear equations in your with three unknowns. So it's like a over defined system, correct? You have three unknowns for each arm. So let's say you have four equations right now. Now you will somehow try to find a good estimates for your unknowns using these four equations. Is it clear? How is the true mean of an arm defined? It's a function of user features. It's a linear function of user features, which is nothing but this, right? So the weights are same. The weights are for a particular arm. The features will change. For every user, the features will change. But the weights are particular to one particular arm, right? Is this model clear to everyone? So we have some function of user features. The function is parameter weights. So every arm has three weights, right? And it's a function of the user features. Is this setup clear to everyone, or is there any doubt? So if you show arm one to four users, you'll get four samples like this. So it's like you get four linear equations. If you this is like an estimation of mu of x, right? So you see these are some real. This is like you have four linear equations in three unknowns. You try to solve these equations and find a good approximation, which will satisfy to a good extent of all these four equations. Then you have some estimates about W1 vector. Like I'll call it as WA1 vector, like the arm1 W vector. Similarly, have for W, right? For arm2, you have three unknowns, right? Corresponding to arm2. WA21, WA22, WA23, right? For every arm. So you solve these three unknowns when you have the data corresponding to arm2. Yeah, yeah. This is a bandit problem, right? So this is supervised learning plus reinforcement learning. Are you understanding that? What, like after you estimate these W's, what you do is reinforcement learning. How you estimate W's is supervised learning, regression. So after you estimate W's, what will you do? Let's say you have done these 8 explorations. Now a new user came. Now you estimated WA1 vector and WA2 vector. What term will you show? What article will you show? No, you do linear regression on this problem. You do linear regression on this problem. You did two linear regressions. Now you got WA1 vector, WA2 vector. Now a new user comes. What term will you show? That is like a greedy algorithm. That if you don't want to do greedy algorithm, you use UCB algorithm. So you have some estimate of the true mean for every arm. Now instead of showing the arm with the highest true mean estimate, highest estimated mean, you show highest estimated mean first plus some epsilon, and show that uh, if you have some totally 1,000 users who are coming to your system, how do you maximize your total return? Like how many people will like your articles? You want to maximize that. If you try to be greedy here, then you will incur a large regret. If you try to explore, let's say epsilon greedy, you show the mm, article with the highest mean, estimated mean with some probability 1 minus epsilon. With probability epsilon, you show some random article. So all those algorithms whichever you have learned before can be used here. So this is like the regression problem is like just taking sample average in over one state bandit. If you look at it only from that perspective, then it's like just averaging. It's not RL, right? So just averaging is what replaced by regression here. After that, whatever you do will be done here also. Is it clear to everyone? If there was a one state, only one state, then they should have become a just averaging part, right? What is the estimate of the true mean of arm one? That is just average over all the rewards that you got. Okay. So I'll give you one assignment question where problem set maybe where you can try this one. Okay. Can you be louder? So if because you don't know which users are going to come, that's what you're saying. Because let's say you have some 1,000 users who are going to come. We don't know which users are going to come. How do we define regret? Is what you're saying. Okay. I think irrespective of what users are going to come, maybe we'll have a regret definition, which is like the worst case among whatever the users like the users. Maybe there will be some set of users who will come, and any some let's say you have T users who are going to come. Those T users maybe can be picked from the user set, and like any T users can be picked, I guess. Yeah, because if you can correctly estimate W1, W2, W3, then whatever user comes, you know what is the best term to give, right? So you know what is the best thing to do. Let's say someone gives you W1, W2, W3. You know what is the best you can achieve for any set of users. You just compare that with whatever your algorithm is doing. So give me any 1,000 users. If I know W vectors, I know what is a best algorithm can do. Compare that with my own algorithm. Okay. Yeah. So this is yeah, we are not going into details of how are we going to analyze this algorithm or what is a good number of times to explore. We are not going into those details because that will take a lot of time. I just wanted you to get a feel of what contextual bandits is and how is it similar to what we have studied till now. So you can, of course, if you want to do a proper analysis of different algorithms and regrets, we'll need a lot more time. But all that I want you to appreciate is at least till greedy algorithm are you able to follow or not? Epsilon greedy. At least implementing that algorithm, not at the level of understanding the regret analysis. Let's at least you know how to implement a greedy algorithm on top of this, right? After every user, you can update your W vectors and you just show if a new user comes, you have some estimates of W vectors for each arm. You just calculate the estimated true mean of that user with respect to all the arms. Whichever arm has the highest estimated reward, you just show that arm. That's a greedy algorithm. Yeah, like a greedy algorithm is that, right? You keep updating whenever you get a sample from an arm, you'll update the estimated reward of that arm, right? Yeah. So if you want to do explore first, then commit, then you don't update. Then you will fix some W vectors for all the arms. Then if a new user comes, you will just use those Ws. You won't update it. So it depends on what kind of algorithm you want to use. All that I want you to appreciate is the similarity to what we have learned till now and the generality compared to that. Like it's a generalized version of that. So for example, if I keep only one feature for each user and I'll just say that feature is always one, that feature will always take value one, then it's like it's normal bandit problem because there is only one state. So just like how we have, it's possible to show that you have to incur at least a regret of root kt into d, where d is the dimensionality of the user features. So it's like root kt into d is what you can show for any algorithm that you do. Like if it's a one feature vector, then it's like root kt, which we know. If d equal to 1, that means there is only one feature. Then you will incur a root kt regret. If your feature vector is of length 3, then you will incur at least root 3 kt or something. So it can be shown, we can construct lower bounds saying that any algorithm will incur at least this much regret on some particular instance. Okay, but we'll not go into all that. So I'll release a problem set where you can try out some simple problem related to this. Okay. So this is about the contextual bandits. Since I did not explain you the linear regression part clearly in the last lecture, I wanted to show you that. So that is fine. Now, uh, in from today's lecture, we'll go into the full RL setup where we don't just have multiple states. We also have this correlation across time. So what action you take in this time slot will decide what state you land up in the next time slot. So for example, in a video game, if you are doing something, if you press some button right now, what image you will get in the next time slot will depend on what button you have pressed right now, right? It's not like the contextual bandit where irrespective of what arm you show to a particular user, the next user who is going to come is not decided by what article you showed to this particular user who came now. At time t equal to 1, one user came, you showed some article to him. It does not decide what user is going to come next. It just decides whether whatever article you showed, whether the user will like or not. That much is decided. In the next time slot, which user is going to come is not affected by what you have shown to the first user. So that is, there is no time correlation across states. The states are independently coming. Like each user will just come. It does not have an effect on what you did before. But in RL setting, so you are in some particular state, you take an action. What state will come next will depend on what you have done before. Okay. So we'll just try to model this uh, uh, relation using using a mathematical tool called Markov decision processes, which is called MDP. We'll see how the full RL setting, which we know, can be modeled mathematically using the framework of Markov decision processes. So we'll look at the full RL setting. So by full RL setting, I mean that there are multiple states. Compared to bandits, these are the differences. There are multiple states and there is time correlation across time correlation for states that you see. States are correlated across time. You can think like that. Okay. Then we'll model this problem as a Markov decision process. Then, uh, like just like for how every arm we had some estimated mean as the value of that arm, right? Similar to that, we'll define what in the MDP setting, what is the value of some action. Okay. The value of an action is not like here, the value of an arm is not just a function of the arm, right? It also depends on the state. Just like in contextual bandits, what is the probability that an article is liked? It's not independent of the user, right? What is the probability that an article is liked by some particular user? That is how we talk. We are not talking what is the probability that an article is liked. It's not independent of the state. What is the probability that an article is liked by a particular user? If the user state is this, what is the probability that he will like a particular article? Right? Similar to that, we define what is called a value function. The value function is in a given state, it's a function of the state which you are in. If you are in some particular state and if you follow some particular policy, what is the how good it is. Okay, we'll look at it. So these are some things which we look at. What is called a value function, what is called an action value function, which is generally denoted by V pi, and this is generally denoted by this is V pi of s. Value function is a function of your state and your policy. Action value function is not just a function of state, but it's also a function of action. Anyway, don't worry about these things. We'll just look at these things in detail. I'm just writing down as to what is going to come today. Bellman expectation equations is one thing which we'll see. So these are the topics which we'll cover today. So if you remember, the full RL setting was like this, right? You have some agent and you have some environment. Like the environment you can think of as a program in a video game, and the agent has some user who is playing different buttons on the video game. And what will the agent see? He will see the screen on the video game, which is like the state at some time t. And then what will happen when the user sees some state st? What will the user do? He will take an action at. And what will the environment do? The environment will give give what? It will give a reward which I denote as RT plus 1. So you can think that the agent will take an action and maybe the environment will respond in T plus 1 with a reward, and it will also give you what? A new state, right? So this is the loop. So this is like you start with some state, you take an action AT and you get a reward and you get a new state. Then again you take a new action and it will continue like this. Okay. And so we want to model this agent environment interaction using some mathematical model. Okay. So for that we'll use a tool called MDP. So maybe I'll gradually introduce what an MDP is for you. So you can, how many of you know what is a Markov chain? Okay, so the good enough, the number of people who do not know. Okay, so maybe I'll first introduce what is a Markov chain, and then I'll introduce what is an MDP. So how many of you know what are independent random variables? Is there anyone who doesn't know? Okay. If you still don't know what is independent random variable, this is a good time to drop. Okay. So independent random variable. So let's say you have some set of random variables. So let's say you have some random variables like this. And when do we say these random variables are independent? So if these random variables are independent, let's say if I condition h, let's say h4 given h1, h2, so on, let's say. So let's say you condition on all other random variables except h4. So this will be equal to what? This will be equal to P of x4. Knowing about other random variables will not tell anything about this particular random variable, right? So Markov chain is somewhat different. So let's say I have some sequence of random variables, h1, h2, so on. You have some sequence of random variables like this. So what these random variables will satisfy a particular property called Markov property. So what Markov property means is, uh, given the present, the future is independent of the past. This is called Markov property. So what it means in this scenario is, if you know where you are, the where you will reach in the future is independent of how you came to your present. So let's say you are in some position right now. What position will you reach in the future is just dependent on where you are currently. It doesn't matter how you came to this present position. Okay. So mathematically, you can write it like this. So this is like probability of ht plus 1 uh, given ht minus 1, ht minus 2, so on, is same as probability of ht plus 1 given what? ht. So you can tell me the whole past about that thing, but all that I care about to predict the future is just the current position. So how I came to that current position does not matter. Okay, only where I am currently that matters. So maybe I'll just quickly give you one example of a Markov chain. So let's say yeah, we are tossing a coin repeatedly, and let's say if you get heads, you will get 1 rupee. If you lose, if you land up in tails, you lose 1 rupee. Okay, I'll just call HT as example of a Markov chain. I'll just call HT as the amount of money I have at time t. Okay. Amount of money at time t. So if I currently have, let's say, 5 rupees, and at some time t, how much money will I have? Let's say for every toss I throw, I get 1 rupee or lose 1 rupee. Okay. If it lands in head with probability p, I'll get 1 rupee. If it lands in tail, I'll lose 1 rupee. Let's say. So if I'm having currently 5 rupees, uh, in the next time slot, let's say ht equal to 5, what will ht plus 1 be? Possible. What are the possible values? It will be 4 and 6. What is the probability that I'll go to 6? P. Let's say the probability of X is P. And what is the probability that I'll go to 4? 1 minus P. Right? So this is like, what is the probability that ht plus 1 equal to 6 given ht equal to 5 is P. Right? So now it's clear, right, why it satisfies Markov property. Because uh, ht minus 1 equal to 4 or ht minus 1 equal to 6 does not matter here. Even if I condition 4 or if I condition ht minus 1 equal to 6, it does not matter. What ht is, that matters for me. What ht minus 1 is does not tell me anything if I know ht. But if I don't know ht, then ht minus 1 is useful for me. If I don't know ht, Even ht minus 1 will tell me something about what ht plus 1 is going to be, right? Because if ht minus 1 is 4, what ht plus 1 can take? If ht minus 1 equal to 4, what are the values that ht plus 1 can take? It can take either 6, if he wins 2, or it can 4, or it can go to 2 also, right? So it's not that ht minus 1 does not affect your ht plus 1. All that I'm saying is, if you know ht minus 1 does not give you any additional information. Okay, that's I want you to appreciate that. It's not that I'm not telling that ht minus 1 is independent of ht plus 1. I'm not saying that. All that I'm saying is, if you know ht, then ht plus 1 has nothing to do with ht minus 1. If you don't know ht, then of course ht minus 1 will give you some information about what ht plus 1 is going to be. Okay. So this is like a typical, like this is an example of a Markov chain where a Markov chain can be represented using some state diagram like this. Like each state is like what are all the values that your random variables can take, and if you are in a particular state, you can check the state where all can you go and with what probabilities you can go there. Okay, this is called the state diagram of a Markov chain. Okay, is it clear to everyone? So you can even write it like using a matrix, saying that what are all the values. Let's say at most you can have 10 rupees in this game, and let's say the game ends there or something. So you'll have the states here. You'll have the states here, and this is everything will tell if you are in state. Okay, Pij will tell you if you are in state I, what is the probability that your next uh, state will be state j. Okay, this is like probability of ht plus 1 equal to j given ht equal to I. If this probability does not depend on t, it's called homogeneous stationary Markov chain. But we will not go into specific details like here. So this matrix will give you the definition of the it will specify whatever needs to be specified about the Markov chain. Okay. If you are in a particular state, with what probability you will go to the next state. For every state, it will tell you that. Okay. This is called transition probability matrix. Okay. So this will be like one. Okay. So this is so this is about Markov chain. Now we'll see what is an MDP. An MDP is like in our RL environment, what next state we'll go into doesn't depend on what state we are in, right? It also depends on what else. What is the next state? It will depend on what all things. What is your current state and what action you take in this current state. It depends on two things. So this Markov chain is just modeling. If you are in some state ST right now, what is state ST plus 1? It is just telling you that much. But we want also action to come into picture. If you are in some state ST, and if you take action AT, then what is the probability that I'll go to some state ST plus 1? That's what I want to capture using MDP. So this is, you just think of this coin toss game, and just let's say we'll modify it a little bit. Here right now we are just saying in every time slot we are just tossing a coin. If you land in heads, you will get plus 1 rupee. If you land in tail, you'll get minus 1 rupee. Right? That's what we are modeling here. So we'll just introduce some action. Let's say this is a gambling game, and in every time slot you have a certain amount of money, and your action is how much amount of money you want to put in the game. Let's say you have 5 rupees. So you can decide whether you want to put all the 5 rupees in the game. If you put all the 5 rupees, if heads come, you'll get 5 more rupees. If It tail 5 rupees, you lose. You will end up with 0 rupees. So you have 5 rupees. How much you want to put in the game is the action that you want to take out of the 5. If you have 5 rupees, you can put 1 rupee in the game. You can put 2 rupees. You can put 3 rupees. You can put 4 rupees. It's up to you. So this is like an MDP. So we have some 5 rupees. And there are multiple actions that are possible in this state. What are those actions? So there are multiple actions that are possible. Let's say one action is like bet 4 rupees. Okay, this is one action. Let's say bet 2 rupees. This is one action, right? So how like there are 5 possible actions, right? How much money I want to put in the game is my action. And what is my next state? If I put 4 rupees in the game, what are the possible next states I can go into? If I bet 4 rupees in the game, what are the possible next states? It will be either 9 or 1. What is the probability that I'll go to 9? P 1 minus P, right? Similarly, if I bet 2 rupees, I can either go to 7 or 3 with probabilities 1 minus P with probability P, right? Okay, so this is what an MDP is. Okay, so at every state you have some certain actions possible. Now your next state is a function of not just your current state. It's a function of if you are in some state ST, given that you are in some state ST and you have taken some action AT, what is the probability that you'll go to some state? That's what the Markov decision process tells us. Okay, so this is like probability, and it's not just that, right? It should also tell you something else. You are in some state, you took an action. What is the next state? That is one thing which it has to tell. What else it has to tell? How much reward are you going to get for doing this? That also it should tell. Okay. So this is model like this. The probability of getting a reward. So a Markov chain, an MDP will have the following things. It will have a state space, and it will have some action space. So this action space could be variable for every state. For example, in our current MDP, the set of actions that you can take in a particular state changes from state to state. Right? If you have 5 rupees, you can bet from 1 to 5. If you have 6 rupees, you can bet from 1 to 6. Right? The set of actions is itself is a function of your current state. Right? So that could be possible, or you can have some set of actions which are common for every state. That is also possible. So let's say it's variable for every state. You think of the set of actions as the union of all possible actions. Okay. Anyway, so we have some action space, we have some state space. Now, what is that we are interested in? We are interested in these things. What is the reward that you will get? What is the next state that you will go into? Given that you are in some state S and you took some action A. Just like how we had PHA for the Markov chain. This is what tells us. If you are in some state S, take action A. What is the probability that you get a reward R and you'll go into some state S dash. So this is nothing but probability of RT plus 1 equal to R comma ST plus 1 equal to S dash given ST equal to S comma AT equal to A. Okay. If you know this for every possible S dash, then you know the Markov decision process completely. Right? For every state action S dash, for every S A S dash R, if you know this probability for all possible values, then that means you completely know your MDP characteristics. Is it clear? For example, for this MDP, we know that for every, like you can think of the reward, like for the other one, like you can think the reward is like that. So then you can calculate, right? For every uh, state action pair, you can calculate the probabilities, these probabilities, right? Now, what is the task? If you know, if someone comes and gives you all these things, how much money you have to bet in each state? What is a good way to bet so that you will earn good money in the long run? That will be your aim, right? So for every state, you want to know what is a good amount of money to bet in the game, right? So this is like policy. If you are in a given state, what action you should take, that is defined by the policy. So a policy could be either a stochastic policy or a deterministic policy. Like this will define MDP characteristics. These will completely define your MDP. Okay, you can think of them as MDP dynamics. Okay, dynamics of the MDP. So a policy is, if it's a stochastic policy, I want to know this uh, probability for every state and action. If I am in some state S, with what probability I should take action A. So this is like a stochastic policy, which is like probability of AT, what action I should take if I am in some state S. Okay, this is a stochastic policy, or you could have a deterministic policy, which is if you are in some state S, just outputting one deterministic action, which is like a mapping from your state space to action space. Okay, this is a deterministic policy. So you can have different kinds of policies, either a deterministic policy or a stochastic policy. And also there are two types of settings in which we study these MDPs. Like there are episodic two types, episodic MDP or continuous MDP. It's a function from state space to action space. If you are in some particular state, it will tell, okay, this is the action to take. Here it is telling, it's not telling a particular action, it is just telling play action one with this property, play action two with this property. Is everyone fine till now? So there are two types of settings in which we study. Episodic MDP will have some state called a terminal state. If you reach that state, the game will get over. Like the episode will terminate. Okay. So this terminates at a special state called terminal state, which we generally denote by ST. Okay. So if you reach this particular state called terminal state, the episode will get over. Okay. So by episode, I mean this sequence of uh, interaction. Like continuing like this. And when you reach this particular state ST, then that episode will terminate. This whole thing is called one episode. Okay. And in continuous MDP, there is no such terminal state. The episode keeps going on forever. Okay. Okay. So these are two types of settings that we have. And in this, in this kind of episode, what is that we want to learn? Like, what is a good policy for us? What is that you want to ideally maximize? So the total reward that you get in an episode is what you want to maximize, the cumulative reward, not just an immediate reward. So the cumulative reward is generally denoted by a term called return. Okay, if you are at so if you start at time t, what is the total future reward that you can get? Okay, so that is nothing but right. So this is the cumulative reward from time t. Okay, so we are just calling the total reward you get from time t as the return. The total reward that you get starting from time t is called as the return, which is denoted by GT. RI is the reward that you is this clear? So for this T is the this T is the random, which is telling you the time at which your episode terminates. You don't know when the episode will terminate. You will keep changing from one state to other state, and when you reach a particular terminal state called when you reach a particular state called the terminal state, then your episode will get over. Okay, you don't know exactly in how many steps you will reach the terminal state. You keep playing the game till you reach the terminal state, and you just count all the rewards that you got. You just add all the rewards that you got till you reach the terminal state. Okay, so t is not some fixed number here. T is the time at which you reach terminal state. It can vary. You start playing the game till episode will terminate at some point. So that time is what we are calling as t here. Okay, so it's a random variable because it depends on how you play the game, right? So if you have 5 rupees, if you bet all the five and if you lose the money, let's say zero is the terminal state. Within one round, you can lose the game. Or if you play well, maybe you'll play for a lot of time and t can be larger. So it's a t is a random variable. Okay. So this is written. So in the continuous setting, this is like the total return that you get till infinite, right? You keep playing forever. Okay. So in this setting, what is one issue that we can face? Your return can be unbounded, right? Because you're playing forever, right? So if you have to sum all the rewards that you get till infinite, then your return can be unbounded. So for that, what people will do is they'll introduce something called a discount factor, like GT can be unbounded. So to solve that problem, what people will do is they'll introduce something called discount factor. Some number between, like gamma is some number between 0 and 1. So maybe let's say, so gamma is some number between 0 and 1. If gamma is less than 1, if gamma is less than 1 and your rewards are bounded, like each reward is capped at some number, then your return is bounded, right? Because it's like a GP, decreasing GP with decreasing ratio, right? So you can interpret gamma as how much emphasis you place as an agent on your immediate rewards versus long-term rewards. If gamma is so maybe first I should define what is GT with respect to this gamma, right? So this GT will be like the immediate reward plus gamma times RT plus 2 plus gamma square times RT plus 3 plus so on. Okay, this is GT. So your immediate reward plus gamma times the next step reward plus gamma square times the next step reward, so on. Okay. So if gamma is 0, what will be GT equal to? If gamma equal to 0, GT is nothing but RT plus 1. So that means you are short-sighted. You just care about the immediate rewards more. Okay. If gamma is closer to 1, you are looking for the long-term gains, right? If gamma is closer to 1, you are keeping good weightage for all the rewards that you get in the future as well. Okay. So depending on the application, if the you can choose your gamma. But this is mainly introduced for our uh, flexibility, in the sense that we want GT to be bounded, but people can interpret it in different ways based on the application. If gamma is closer to 0, then you are more caring about the short-term gains. If your gamma is closer to 1, you are far-sighted, in the sense that you care about the long-term gains. You keep equal emphasis both on the short-term and the long-term gains. Okay. So a good policy will be the policy which will try to maximize the uh, expected GT. GT is the total return that you will get. A good policy is a policy which will maximize your expected GT. Okay. So if you want to, so this is not, I'm not writing it very formally, but the goal is roughly like this. You want to find a policy 5-star, which is like the best policy with respect to your okay. So you want to find a policy which maximizes your expected return. Okay. This is what you call as a good policy, a policy which will maximize your expected return. Okay. So it has to be defined more carefully. Right now, you just think of it as a English word. Okay. So if you want to model your bandit problem as an MDP, how will it look? Let's say I want to draw the bandits is a special case of MDPs, right? If you want to model the bandit as an MDP, how will it look? There will be one state is okay, the simple bandit problem, and let's say there are two arms. There are two actions that are possible. Okay. So this solid dot represents one action. Okay. So there are two possible actions in this given state, which are represented by two solid dots like that. And in bandit, of you can think of it as one episode is like one arm playing one arm. You will get a reward, and your episode will terminate. You can think like that. So it's like there is a terminal state. So there is a terminal state. So whatever action you take, let's say there are two arms, arm 1 and arm 2. What you always be in some status, and let's say there are multiple arms which are there with you. Irrespective of what arm you play, you will go to terminal state and the episode will terminate. Okay. And this will terminate with probability 1. Okay. Whatever you are in, so there's only one state. You just take an action and you'll get a reward and the episode terminates. So your return is nothing but your reward for that time step. So it's like if you play one more time slot, if you are playing the arm one more time slot, that is like you are playing another episode. You can think like that. So we have totally T episodes. We want to maximize, minimize the regret over those T episodes. That's how you can think of as the bandit problem. Okay. You are in some status, you take an action, you'll get a reward, and your episode terminates. Okay. So here, what is the best policy means what for us? Because GT is what? GT is the uh, reward for taking that action, right? So GT is nothing but what is expected GT in the bandit setting? The expected reward for playing that particular arm, right? No, you think of it as multiple episodes. So one way is you can think of it as a continuous continuous MDP where you come back to the same state again and again. That's one way to think about it. Like you take any action, you will just remain in the same state. You again take one more action, you will just again come in the same state. That termination is like the T, capital T, you mean? Yeah, that is one way to think about it. But this is, if you want to understand the regret definition clearly, like if you want to later study about regret in an MDP, you talk about you are given some T episodes. You do whatever you want in these episodes. You want to maximize the total reward, total returns across these T episodes. An episode is till you reach a terminal state. You start at some state, you reach an episode. The episode terminates when you reach the terminal. Yeah, that's what I was saying. Then you cannot call it as an episode, right? Like episode won't end with one action. Here, I just wanted to look at it like one episode is like one action. Okay, because the regret definitions for MDP will be modeled like that. You are having T episodes. You can do whatever you want in these T episodes, but you want to maximize your total returns across these T episodes. Okay. T times terminal states. You'll reach the terminal state T times. Okay. But as we'll see that in the MDP, full MDP, analyzing the regret is a much more complicated problem than analyzing the regret on a bandit problem. For example, in the MDP problem, if I give you these numbers, if I give you all these numbers, even if I, for example, for the gambling problem, you know these numbers, right? You know, for every action where you land, you know, with what probability you land, you know, with what reward you'll get, everything you know, right? In problem. That means even then it's not an easy problem to solve. It requires some effort. Okay. But in the bandit problem, what does what do we mean by knowing that? That is like we know these things, right? Probability of R given S comma A. We know this for every S comma A. Right? That's what knowing about the dynamics means, right? Knowing P of S dash comma R for every S comma A. That's what knowing about MDP means. So similarly, if I talk about knowing the dynamics for this MDP, what does it mean? I know the underlying arm distributions, right? That's what it means, right? For every action, what is the probability that I'll get a reward R? That means I know what? I know the underlying distributions of each arm. Is it clear to everyone? Knowing this thing means what? Knowing that thing means for every action, I know what reward I'm going to get. Like the probability distribution, I know. If I know this, I can calculate expected reward, right? If I know this for every arm, I can calculate expected reward. Then what is the best policy? You calculate the expected reward for all the arms. Then you play the arm with the highest true like expected reward. So solving the MDP, if you know this dynamic, is kind of trivial problem in the bandit setting, right? If someone comes and gives you all the distributions of all the arms, then you'll just calculate expected reward for all of these distributions, and you play the arm with the highest expected reward. There is nothing to solve. But in the MDP, as we'll see, even if someone comes and gives you all these things, still it's not easy to solve. You need some effort. Okay. At least you are able to appreciate, right? For bandit, there is nothing to solve. If you know the dynamics of the MDP of the bandits, then there is nothing left to solve. You just calculate the expected reward for each of those probability distributions, and the best policy is the policy which has the highest, which plays that particular arm with probability 1. You always play that best reward arm. Okay. But in this full RL setting, it's requires some effort. Okay. This is like a banded MDP. If we know the dynamics, these are like dynamics. If we know the dynamics, solving the bandit problem is trivial. solving the banded problem is trivial. Okay. Now in MDP, this is like we can just calculate the expected reward for each arm and then we'll play that. That's all. So in MDP, what we'll do is the following. So for an MDP, even if we know the MDP dynamics, even after knowing the MDP dynamics, solving it is not easy. Finding the optimal policy is not so trivial. Okay. So we have to introduce some notation, some definitions to even define what is an optimal policy and properly, and to find some algorithm to find the optimal policy. Okay. So as I mentioned, we'll define some definitions like this. What is a value function? Okay. So the value function of a policy pi. So if you start in some state S and follow policy pi till you reach the terminal state. You start in some state S and keep following policy pi. Okay. What is the expected return that you'll get is defined as value function of that policy. Okay. So for every state, you'll have a different value. Because if you, let's say in the gambling game, if you start at some initial rupees of 100, you'll have a different value. Total return that you'll get will be different. If you start with, let's say, 1 rupee in the game, you will have a different return, right? So the total return that you'll get will depend on where you start. If you start with 100 rupees of capital, the game is going to be different. If you start with 1 rupee, it's going to be different. So this value function of yours is and what policy you follow. So for every policy, if you follow a policy pi starting from state S, what is the expected return that you'll get is what is called as a value function. Expected value of GT given what? What should I write in the given? ST equal to S, right? So this is like the total. This is the total return that you'll get by following policy pi starting from state S. Okay. So there is something called action value function, which is the following. This is like you are in some state S right now, and you have already decided that you are going to take action A right now. You are in some state S, and you have already decided that you are going to take action A in this time step. And from the next time step, I'm going to follow policy pi. Okay. So you are in some state ST equal to S, and you already decided that you are going to play some action A, and from time t plus 1, you are going to follow policy pi. What is the total return that you'll get? Expected return given that ST equal to S and AT equal to A. Okay. In the current step, you will follow action A, and from next time step, you will follow policy pi. What is the total return that you will get? Okay. Now, can someone write V pi of S as a function of Q pi? Let's say pi is a deterministic policy. What will be V pi in terms of Q pi? Is it correct? If pi is a deterministic policy, V pi of S is nothing but Q pi of S comma pi of S. What is V pi telling? In every step, you follow policy pi. So even in time step t, you follow policy pi. Later also, you follow policy pi, right? Because this is when first you follow actually, then the next step you follow policy pi. Even in the time step t, you have to follow policy. So that is nothing but Q pi of pi of S. If pi was a deterministic stochastic policy, what will it be? You have to sum over all possible actions with multiply with the corresponding probabilities. Okay. And so it will look like this. It will look like q pi of s comma a into probability of what? A given s. Correct? If it's a stochastic policy, we'll the second equation. If it's a deterministic policy, we'll get the first equation. Right? Can we write v pi also as a function of q pi? Like q pi also as a function of v pi? Huh? Can you repeat? Yeah, in the current step. Yeah, yeah. That's why I told the current axis is also pi. Okay. So uh, in the uh, in the next class, what we'll do is we'll try to relate. We'll try to come up with some fixed point iteration for v pi. Okay. We want to find an optimal policy. We'll what we'll do is we'll write an fixed point iteration in v pi, so that if you solve that equation set of equations, you learn what is the best value function that can be assumed. Okay. Based on that, we'll do something. So we'll look at what some algorithms called value iteration and policy iteration. So these are two popular algorithms. These are like dynamic programming algorithms on this MDP. Okay. So if you have studied about dynamic programming somewhere, maybe you can briefly revise it. In your data structures course or somewhere you might have, or algorithms course, you might have read about dynamic programming. So if you have read about that, you can revise and come. Okay. Okay. Thank you.